Hello everyone, my name is Ramya. I'm a postdoctoral student under Professor Grace Gao in Aeroastro Department at Stanford University. The topic of my today's presentation is on a case study analysis for designing a lunar navigation satellite system with time transfer from Earth GPS. As we are all well aware, recently there has been a significant drive towards establishing a sustainable lunar presence with more than 40 missions being planned in the next decade. To support these increasing activities, reliable positioning, navigation, and timing, in short known as PNT, is needed everywhere on the moon. Given this, active efforts are being invested in exploring the feasibility of an Earth-like GPS around the moon. Some examples include NASA's LunarNet, the Moonlight Initiative by the European Space Agency, and some rich simulation studies. Also, there has been a growing interest in using small sat platform for the future lunar PNT constellation. Given that these initiatives are in their preliminary design phases, many decisions are not yet finalized, such as constellation, orbit, transmit antenna, onboard clock, and so on. As illustrated in this figure on the left, the designed lunar navigation satellite system, in short known as LNSS, is expected to achieve a certain level of positioning accuracy on the lunar surface. While this positioning accuracy depends on a variety of different factors, a few key ones are pointed out in this table. First is the Lunar User Equivalent Ranging Error, or UERE, which provides insights regarding the ranging accuracy of the signals transmitted from the LNSS satellite. Second is the minimum receive power, which governs the signal acquisition and tracking performance. The next ones are the number of LNSS satellites and the geometric dilution of precision, or GDOP, both of which ascertain the covariance of the position estimate. Last is the overall cost, which depends on the constellation size, launch and orbit injection costs, onboard equipment, and their maintenance costs. To provide a systematic approach, the focus of our current work is on assessing the LNSS design from the perspective of lunar UERE. On the other hand, accounting for these other factors will be explored in our future work. An important design choice for LNSS is regarding the type of lunar orbit. Several orbits have previously been investigated for their stability, of which a few examples are illustrated in this figure and also listed in this table. One is the elliptical lunar frozen orbit, or ELFO in short, which provides a good coverage of the lunar poles and maintains nearly constant orbital parameters. The next one is the prograde circular orbit, or PCO, which exhibits multi-year stability. The low lunar orbit, on the other hand, exhibits quasi-frozen characteristics at certain inclinations. The last one is the near rectilinear halo orbit, or NRHO, which has high visibility of the lunar poles but requires more frequent station keeping than the other orbits. Another important design choice for LNSS is regarding the grade of onboard clock. This choice is particularly crucial because the timing stability of the onboard clock directly affects the ranging precision offered to lunar users. Some popular choices of atomic clocks are listed here in the increasing order of their timing stability. Observe that as the timing stability increases, the size, weight, and power, collectively known as SWAP, increases as well. Among these different clock choices is the low SWAP chip scale atomic clock, or CSAC, which is commonly used for near-Earth space applications. Another notable clock on the higher end of the SWAP spectrum is the Deep Space Atomic Clock, or DSAC. This has been recently developed by NASA to assist in spacecraft radio navigation-based applications. Also note that these orbit and clock choices are further influenced by additional challenges that are incurred while designing a small SAT-based LNSS. Some of these challenges include limited payload capacity, restricted ground monitoring network, and high lunar orbit perturbations. Given this, one may consider the potential in leveraging the existing legacy Earth GPS signals to alleviate the LNSS design challenges. In this context, Rich simulation studies and preliminary satellite missions have been conducted to confirm the tracking of Earth GPS signals using a high sensitivity receiver. This high sensitivity receiver is required to account for signal attenuation at large lunar distances and Earth occultations as illustrated in this figure. Also, based on our simulation analysis, which is shown in this figure, we can observe that for certain chunks of time, as seen here, 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 and here, the received CN0 values are greater than a certain pre-specified threshold. This implies that successful acquisition and tracking is possible at lunar distances in an intermittent manner. With this high-level idea in mind, in our prior work, which was presented at the ION GNSS Plus last September, we designed an LNSS architecture that harnessed the Earth GPS signals to estimate the timing corrections for the lower grade onboard clock. An illustration of this concept is shown in this figure. More specifically, we designed a timing filter that corrects the clock estimates when Earth GPS signals are available. We also developed a relevant metric known as Earth GPS Continual Outage Period, in short ECOP, to analyze the visibility effects on the timing stability. We also devised a lunar UERE metric, which primarily depends on the root mean square error from our timing filter. Given that many design choices among orbits and clocks are yet to be finalized, in this work, we analyzed the trade-off in designing the future small sat-based LNSS with time transfer from Earth GPS. For this, we simulate an LNSS satellite in various lunar orbit types, including ELFO, NRHO, LLO, and PCO, and equipped with diverse swap clocks such as CSAC, PRS-10, MAC, RAFS, and DSAC. We also examine how the lunar UERE metric is affected by varying the rates of processing available Earth GPS measurements. Intuitively, this analysis provides insights into power required for operating Earth GPS receiver to get sufficient ranging precision on the lunar surface. The outline of the presentation is seen in this slide. I will first explain our case study on Earth GPS to LNSS time transfer. Next, I will demonstrate our algorithm's performance in terms of lunar UERE across various case studies that are generated using simulated experimental data. In the end, I will summarize my talk. Now let's look into the details of our case study on Earth GPS to LNSS time transfer, starting with our timing filter framework. We designed a timing filter to estimate the bias and drift of the onboard clock. Particularly, we execute time update every t-predict seconds to propagate the most recent clock estimates forward in time. Next, in addition to considering the Earth GPS signals, we aid the measurement update using known LNSS satellite ephemeris. Given these inputs, we first analyze the Earth GPS continual outage period, in short known as ECOP. During no ECOP, that is when Earth GPS signals are available, we perform measurement update every t measure seconds to correct the clock estimate. As shown here, we set t measure to be a value greater than or equal to t predict by a factor of m. For intuition, as m increases, the Earth GPS signals are less frequently utilized, thereby allowing the receiver to switch off for longer time and save onboard power. We also devised the mathematical formulation of lunar UERE, where UERE stands for User Equivalent Ranging Error. For this, first note that unlike Earth, the Moon has no atmosphere and building infrastructure. So the lunar UERE does not require to factor ionospheric, tropospheric, and multipath effects. Having said this, as shown in this equation over here, the RMS errors to be included in the lunar UERE are the broadcast clock, the differential group delay, broadcast ephemeris, and receiver noise. More specifically, the component related to the broadcast clock depends on our time transfer that in turn depends primarily on the case study of orbit and clock considered. As a side note, we set these other sources of error in lunar UERE as constant predetermined values. In this work, we investigate a total of 20 case studies using 4 orbits listed in this table over here, and also 5 clocks listed in this table over here. Note that each case study is framed using an orbit clock pair. In regard to lunar orbits, we generate an NRHO whose maximum altitude extends up to 78,000 kilometers. The time trajectory of this NRHO is illustrated in this moon inertial frame over here, while the other 3 orbits in the same reference frame are shown over here. In particular, we model LLO, shown in magenta, to be in a circular orbit at an altitude of 100 kilometers, PCO in blue at 3,000 kilometers, and ELFO in orange at 9,700 kilometers. On the other hand, we consider 5 clocks that include CSAC, MAC, PRS-10, RAFS, and DSAC, whose timing deviation over a day range between 1.5 microseconds to 4 times 10 power negative 5 microseconds. Now I'll talk about our simulated experimental results that analyze the trade-offs among these different case studies. For an experiment time duration of 2 months, we considered a simulated Earth GPS constellation with 31 satellites. We modeled the transmit antenna gain pattern for each GPS satellite by utilizing the results from the NASA's antenna characterization experiment. An example of the modeled main lobe and the side lobes from block 2RM are shown on this in this left figure. We utilize the Systems Toolkit software, in short known as STK, to model satellites and the attenuation of Earth GPS signals based on occultations and path loss. This STK animation shows the intermittent availability of Earth GPS signals in ELFO, where the magenta lines originating from the LNSS satellite indicate the visible Earth GPS satellites at any given time instant. Next, in terms of settings for the simulated Earth GPS receiver, we consider CN0 threshold and receiver tracking time such that any Earth GPS satellite is considered visible if CN0 is greater than 15 dBHz for at least 40 seconds. Given that there exist no standards on the target lunar UERE values to be maintained, we evaluate our case studies for various potential values of 5 meters, 10 meters, and 30 meters. We set an error covariance of 3 meters for LNSS satellite position, which is used for aiding our filter and also lunar UERE computation. We also conduct sensitivity analysis by varying our measurement update rate between 60 seconds to 60 minutes. In the first set of experiments, we compared different lunar orbits for their maximum Earth GPS continual outage period, percentage of time for which number of visible satellites are greater than or equal to 1 and greater than or equal to 4. An illustration of LLO is shown on the right, where blue indicates the number of visible satellites and red vertical bars indicate ECOP segments. We observe that LLO, which has a maximum ECOP of 2,880 seconds, exhibits the smallest time spacing between consecutive ECOPs. Intuitively, orbits exhibiting least maximum ECOP and greater satellite visibility are favorable for LNSS design. These conditions are satisfied by the NRHO, which demonstrates 99.9% satellite visibility and a maximum ECOP of only 420 seconds. This is justified because an LNSS satellite in NRHO operates at very high altitudes and therefore experiences fewer occultations from both Earth and the Moon. In this third set of experiments, we showcase the variation in lunar UERE computed from our time transfer across different case studies. We set the measurement update rate to 60 seconds, which is same as the time update rate of 60 seconds. We validate that our computed lunar UERE exhibits a low value of less than 10 meters for most case studies, except the one involving LLO and CSAC, which is at 18.4 meters. While the statistics for least maximum ECOP and greater satellite visibility favored NRHO earlier, these comparable results of the lunar UERE implies that the lunar UERE depends on other factors as well, such as the orbital parameters that govern the Earth GPS to LNSS geometry. Let's make some additional observations. For instance, if the target lunar UERE is to be maintained is less than 10 meters, we can easily opt for low swap clock like CSAC or MAC instead of higher grade clocks like DSAC. Similarly, we can also choose more stable orbits like PCO or ELFO instead of the harder to maintain ones like NRHO. On a different note, we observe the potential for a heterogeneous small sat-based lunar PNT using our time transfer technique. For instance, let's consider another target lunar UERE, say less than 5 meters. From our case study analysis, we observe that a viable LNSS design based in ELFO and LLO can be constructed, where the satellites in LLO can be matched with a PRS-10 clock, while the ones in ELFO can be equipped with MAC, which is a lower swap clock. In these final set of experiments, we show the computed lunar UERE across all case studies for 3 reduced measurement update rates, that is 5 minutes as shown here, 30 minutes as shown here, and 60 minutes as shown here. Comparing this region over here to this one over here, we observe that low swap clocks with more frequent measurement updates exhibit a higher sensitivity in computed lunar UERE across different orbits. We also demonstrate that our time transfer technique satisfies a lunar UERE of less than 30 meters for Earth GPS measurement update rates up to 30 minutes. This performance is comparable in the order of magnitude to that of baseline update rate of 60 seconds and also the legacy Earth GPS constellation. To summarize, in this work, we performed an exhaustive case study analysis for designing a small sat-based LNSS with time transfer from Earth GPS. In particular, we investigated the trade-offs related to onboard clocks and lunar orbits. Using high-fidelity simulations in the SDK software, we designed a total of 20 case studies based on 4 orbits and 5 clocks. We validated that NRHO exhibits greater satellite visibility of 99.9%, and using low swap clocks and more stable orbits, we demonstrated lunar UERE of less than 10 meters for high measurement update rates of 60 seconds, and also lunar UERE of less than 30 meters for reduced measurement update rates of up to 30 minutes. We want to thank AGI Educational Alliance Program for providing us with the Systems Toolkit software license. We also want to thank the members of NavLab for their insightful discussions. Thank you.